In this video, we have some more results in elementary number theory. We have second result which states that if n is AB, where a and b are relatively prime, then Euler's phi function of n is the phi of a and phi of b. That is, phi of n is equal to phi of a into phi of b. So we shall take what is given to us, that is n is AB with a and b to be relatively prime. Then by the fundamental theorem in arithmetic applied to a and b, this is what we have: a to be product of prime powers and b to be product of prime powers. Here the prime numbers are taken as p1, p2 and so on pk, and here the prime numbers are taken as q1, q2 and qr. Now applying the first result, that is formula for Euler's phi function, this is what we have: phi of a is this and phi of b is this. Now we consider first the RHS. So we have phi of a into phi of b to be this into this. This is what we have. So we have AB into all these terms we have. Now we'll go to LHS. Again, by the first result, that is formula for phi of n, we have phi of n, which is phi of AB. AB is what? AB is this into this. So we have this, and we have, according to the formula, whatever you had here, you have that is to be written, and then into whatever prime numbers that we have, that has to be written as the product in this way: 1 minus 1 upon p1, 1 minus 1 upon p2 and so on, 1 minus 1 upon pk, into you have this. For these terms we need to write, so this is what we have. And this is nothing but a, this is nothing but b, so ab into this we have. And from here RHS, this LHS we have to be RHS. So we have this result that whenever a and b are relatively prime, then phi of AB is phi of a into phi of b. So next we will find the sum of all positive integers less than n and relatively prime to n, and that is shown as phi of n upon 2 into n. So you have phi of n by 2 times n to be your sum of all positive integers less than n and relatively prime to n. So first we will introduce this set, the set of all positive integers less than n and relatively prime to n. So that is denoted as u suffix n. So by the definition of phi n, obviously the number of integers, this gives the what are the integers less than n and relatively prime. Then how many of them are that is denoted as Euler's phi function phi of n. So naturally the number of elements in un is phi of n. The number of elements in un, we call it as order of un. So we have phi of n to be the number of elements present in un, that is the order of un. So they are nothing but the number of integers less than n and relatively prime to n, and that is your Euler's phi function phi of n. So now to prove the main result, we have the sub result which states that whenever x is a number which is relatively prime to n, then n minus x will also be relatively prime to n. So suppose we assume that this is not true. We want to establish this, so we'll assume the contrary and arrive at a contradiction. Suppose n minus x and n are not relatively prime, and suppose they have a common divisor, say d, which is different from 1. If it is 1, then we have if that is only the common divisor, then we are finished, we have the result. So we consider some d which is different from 1 to be a common divisor. Then common divisor we have said, so d must divide n minus x, d must divide n. So d divides n minus x and d divides n. Now these two together imply that d divides n minus x. So that is because we have already seen in a result in the first video that if d divides C divides a, C divides b, then c must divide a minus b. So using that result, we have this. The proof of this is already given. So we make use of the result. So this is what we have. So d divides x. Already d divides n. Now you have got d dividing x. So which means that n and x, or rather x and n, have a common divisor d, which is different from 1. But that contradicts the given condition that x and n are relatively prime. So thus d becomes a common divisor for x and n. But this contradicts this assumption that x and n are relatively prime. So we conclude that because of this our assumption is wrong, we conclude that n minus x and n are also relatively prime, and that proves the sub-result. So thus in un, whenever x is less than and relatively prime to n, n minus x is also less than n and relatively prime to n. And not only that, when you add this x and n minus x, that will result in n. So these elements in un are grouped into pairs, namely x, n minus x, y, n minus y, z, n minus z, and so on. So it is grouped in this way. In such we have our sum, the sum of these two, sum of these two, and sum of these two to be n. But we know pretty well that there are phi of n elements present in un. So when you group them into pairs, we have phi of n by 2 such pairs, and each pair, when we sum up, gives n. So the sum of all these divisors must only be phi of n by 2 times n. So as there are phi of n numbers in un, the terms are grouped into phi of n by 2 pairs with their sum n. Therefore, the sum of numbers in un is phi of n by 2 times n. So suppose we consider this n to be 10, then we know that 1, 3, 7, 9 are the numbers which are less than 10 and relatively prime to 10. So phi of 10 is 4. We consider the sum 1 plus 3 plus 7 plus 9, which is 20. And now we compute our phi of n by 2 times n. So phi of 10 by 2 into 10. Phi of 10 is already, we have 4. So we have 4 by 2 into 10. So cancelling this 2 with 10, we have 5. So 4 into 5, that is 20. So as a continuation of the previous result, we have this result: the arithmetic mean of all positive integers less than n and relatively prime to n is n by 2. Now by the previous result, the sum of all positive integers less than n and relatively prime to n is, it is the sum of all positive integers less than n and relatively prime to n to be phi of n by 2 times n. And we want to find the arithmetic mean of them, and we know pretty well that there are phi of n such numbers, and therefore phi of n by 2 times n whole thing divided by phi of n. We want to find the arithmetic mean. So we have the arithmetic mean of all positive integers less than n and relatively prime to n to be this: phi of n by 2 times n whole thing divided by, because there are phi of n such numbers. And cancelling this, we have n upon 2 to be the arithmetic mean of all positive integers less than n and relatively prime to n. Next, we have this result: if I am given n to be a composite number by fundamental theorem on arithmetic, it could be written in this way. So what we are trying to prove in this result is the product of the divisors of n. So already we have seen number of divisors, sum of divisors, and this tells about the product of the divisors of n. Now we'll consider n to be this, because any number n by the fundamental theorem on arithmetic can be written in this way. Now we note that whenever x is a divisor of n, then n by x is also a divisor of n. Similarly, if y is a divisor of n, then n by y is also a divisor. Similarly, z is a divisor of n, n by z is also a divisor of n. And when we consider the product, here we need the product. So when we consider the product, it is by multiplying these two, we are left with n. Multiplying these two, we are left with n. So how many such numbers will be there? How many ever divisors are there, so many such n's will be there. So when we find the product of the divisors, so we will have that n, how many times that we will have. That should be the number of divisors time by 2, because number of divisors is given by a plus 1, b plus 1, c plus 1 and so on, that product. But those divisors are grouped like this: x n by x, y n by y, and z n by z. So when we group them into pairs, how many pairs will be there? A plus 1, b plus 1 into c plus 1 by 2. So many pairs will be there. So the product of each pair is n. So when we consider the total product of the divisors, it will be n to the power. How many pairs that you have? N to the power. That will be the product. So it is known that there are n, a plus 1, b plus 1, c plus 1 number of divisors of n. So these divisors are grouped into these number of pairs whose product is n. And therefore the product of the divisors of n is this. Now we have this last result. If d1, d2, dr including 1 and n are the divisors of n, then the sum of these we can find for each number I-5 function. You find their sum, you will result in the given n. So that is the statement of this result. Now we'll consider n to be, given any n, it can be written by the fundamental theorem on arithmetic like this. Now any divisor d of n is of the form p power x, q power y, r power z. So because we know that any number can be written as product of prime powers, so we have like this, any divisor to be. But how about x? It can be 0, it can vary from 0 to a. And similarly y can range from 0 to b, and z can range from 0 to c. So when we consider phi of d, by result 2 you can, so this d is nothing but this, it can be rewritten in this way. So that is by using result 2. Now we consider this expression. Now the procedure is similar to that of when we found the number of divisors and the sum of divisors. So the procedure is the same. So we consider this product, and in that first we consider this alone. So we have phi of 1 plus phi of p plus phi of p square and so on. This is nothing but 1 plus p minus 1. Phi of a prime number is p minus 1, and this is nothing but whatever number that you have, that into p square into 1 minus 1 upon p. So that on simplification will give you p minus 1 by p square by p. Already at the outside you have p square. So that p square and this p will get cancelled, giving only this p into p minus 1. So that is p square minus p. So in the same way, using the formula for phi of n, these terms are written. So we have this is actually p power a. So 1 and minus 1, p and minus p. So like that all these terms will be cancelled, giving only p power a. This should be p power a. It's a mistake here. So p power a. So this term alone, when we consider it, amounts to p power a. And when we consider these terms in the same way, that will be nothing but q power b and so on. So we have the terms in phi of di's are the terms in the above product, and therefore summation phi of di is nothing but this product itself. And in that product we have each one to be p power a, q power b, r power c, but that we have taken as n. So the proof is similar to that of this. To know the each terms what we have, in this case what we said, 1 comma p comma p square and so on, like that, product taken 2 at a time, pq, then qr, all that, and then pqr. So like that, when you put comma in the product you get the terms. So, and then when we actually consider the continued product, we will get the sum of the divisors. So here we want to find summation phi of di. So the same technique is used here to obtain this. So there, in this case, we considered 1 plus p square and so on. Here we consider phi of 1. We know that phi of 1 is 1. Phi of 1 is nothing but 1. So we have phi of 1 plus phi of p and so on, phi of p per a. When you consider the product of all this, you will get the terms like this only. The arbitrary term and the product will look like this only. So, and this is nothing but phi of d. So there are so many such divisors, they are accounted in this product. We want to find the sum of them, which means we need to find the product. This sum for continued product, that is what we need to have, and that we find to be p par a, q par b, r par c, and that is nothing but n. So summation phi of di ranging from 1 to r, we have that to be n. Thank you.